Jupiter is one of the strangest planets in our solar system. It's massive, but not massive enough to qualify as a star. And while it does orbit the Sun like a typical planet, it gives off way more heat than it gets from our star. Where could this mysterious energy be coming from? We'll tackle that and other thought-provoking questions in today's episode, so let's get started. The reason that Jupiter is so intriguing is because it does and act like the planets we're most familiar with. For starters, it's far too big. The largest gas giant in our solar system is around 318 times the mass of Earth, and that makes it more massive than all of the rocky worlds in our solar system combined. In fact, only two objects in our solar system are more massive than Jupiter, the Sun and the recently discovered asteroid named Makemake. And Jupiter isn't just big in terms of mass, it's also the largest planet by volume. If you could somehow hollow out the Earth and put it inside Jupiter, you would need over 1,300 of them to fill up the giant gas planet. Jupiter is so large that if you were to measure the Sun's diameter and use that as a unit of measurement, the gas giant would still be over 11 times larger. As a result of its enormous size, Jupiter has an extremely strong gravity compared to Earth. It's about 4 times stronger. But the fact that it's so massive doesn't explain why it gives off so much heat. That's actually pretty easy to understand. The more matter you have in an object, the more particles there are inside it. And the more particles you have, the higher the likelihood that they'll collide and release energy in the form of heat. And due to its sheer size, Jupiter has plenty of particles that collide and release a lot of energy. In fact, scientists estimate that there are around 126 quadrillion collisions happening on Jupiter every second. That's enough for the planet to give off around 75% of the total heat we receive from our solar system. In other words, if Jupiter had its own light source, it would be the brightest thing in our night sky. But that's not the case. Jupiter doesn't have a light source. And while it does reflect some sunlight, it can't account for the tremendous amount of heat we observe coming from the planet. We know that Jupiter receives about 24 times less sunlight per square meter than Earth, and yet measurements from NASA's Juno probe revealed that the top layer of the atmosphere is about 60 degrees Celsius hotter than expected. In other words, the average temperature of Jupiter's atmosphere should be closer to minus 145 degrees Celsius, but instead it hovers around minus 88 degrees Celsius. That means Jupiter radiates more heat than it receives from the Sun by a factor of 3. What could be causing this mysterious phenomenon? Scientists have a few ideas, and one of them involves a process that happens deep inside the planet. As you may already know, stars produce energy through nuclear fusion. They essentially take hydrogen and convert it into helium, giving off massive amounts of energy in the process. Well, Jupiter could be doing the same thing, except instead of hydrogen, it's converting ammonia into hydrazine and releasing energy. But for that to happen, the pressure deep inside the planet would need to reach 20 gigapascals. And scientists aren't sure if that's really the case. After all, no probe has ever traveled that deep inside Jupiter. Unfortunately, there's another problem with this idea. It requires temperatures as high as 10,000 degrees Celsius. And that doesn't seem likely given what we currently know about Jupiter's interior. There's another theory that might make a bit more sense. It suggests that Jupiter is slowly contracting under its own gravity, and that process releases energy in the form of heat. To be fair, we don't exactly know how much heat this would produce. Estimates vary widely depending on how fast the planet is contracting. But even if we assume that it's contracting at the slowest possible rate, it would still give off more heat than it receives from the Sun. In other words, we do and need to look for a mysterious reaction taking place inside the planet to explain the excess heat. All we need is for Jupiter to be slowly squishing itself, but is that really what's happening? Ironically, there's some evidence pointing to yes, but it also points to no. According to this theory, the process of gravitational contraction should make Jupiter shrink over time. And that does appear to be what's happening. Observations made by NASA's Juno probe indicate that the planet is shrinking by about 1 kilometer every year. But there's a problem with this explanation. If Jupiter is actually contracting, it should be spinning faster. That's because as the planet gets smaller, the conservation of angular momentum causes it to spin faster. Basically, imagine if you took a spinning figure skater and slowed her down. As she pulled in her arms, her rotational speed increased. Something similar should be happening to Jupiter. Yet observations have found that it's not spinning any faster. In fact, it appears to be slowing down, so it looks like we won't be settling this debate anytime soon. What do you think is powering Jupiter's mysterious energy? Let us know in the comments below, and while you're down there, be sure to subscribe for more videos like this one. One of the coolest things about space is that it never ceases to amaze us. Take black holes, for example. These enigmatic objects are some of the most fascinating things in the universe. And one of the reasons for that is that they have such a profound effect on space and time. Near a black hole, time slows down dramatically compared to an observer who isn't close to one. This phenomenon is known as gravitational time dilation. Einstein's theory of general relativity predicts that the closer you get to a black hole, the slower time will pass. And now an international team of physicists has conducted an experiment that confirmed this effect. They used a device called an atomic clock, which is the most accurate type of clock ever created. One was sent into space on a rocket while the other stayed on Earth. And after 382 days, the team compared the two clocks and found that the one in space had aged slower than the one on Earth. Specifically, it had lost 27 nanoseconds, or 27 billionths of a second. Now, it's important to note that this is a tiny change. But the fact that it happened at all confirms Einstein's prediction. And it also gives us a better understanding of how space and time interact near black holes. Speaking of black holes, have you ever wondered what would happen if one ripped apart a planet? It's a dramatic thought, but it's also a scientifically interesting one. The new simulation from the University of Warsaw suggests that a planet destroyed by a black hole wouldn't just be torn apart, it would actually be completely evaporated. This evaporation would happen as a result of a process called synchrotron radiation. When charged particles are accelerated, they emit electromagnetic radiation. And when a black hole tears apart a planet, the particles in the planet's atmosphere would be accelerated to high speeds. That would cause them to emit a tremendous amount of radiation, literally ripping the planet apart from the inside out. And finally, if you love learning about space, be sure to check out our video on the James Webb Space Telescope. It's one of the most exciting developments in astronomy in recent years, and we can't wait to share our knowledge with you. Thanks for watching.